Okie dokie, okie dokie. Welcome back, everybody. We're going to do another exciting round of reading the PowerPoint. So this is the information Mr. Patrick has selected for us to have a look at. Just going to get my pen sorted. It doesn't let me do it until I start recording. I've figured out the wily ways of the computer now. All right, so something we have to know: the structure of the atom. It doesn't make sense, electricity, unless you know the structure of the atom. Now, the basics of it is this. Most of the mass is in the nucleus, and electrons are free to move. Electrons are negative, and the nucleus is largely positive, with a little bit of neutral in there, but overall the charge is positive. An atom has got a positively charged nucleus containing protons and neutrons surrounded by negatively charged electrons and shells. The nuclear radius is much smaller than that of the atom. It's 1 times 10 to the minus 10 meters, and with almost all mass of an atom concentrated in the nucleus. An atom contains equal numbers of protons and electrons when neutral. Otherwise, it's an ion. Atoms have no overall electric charge because the number of positive protons equals the number of negative electrons when neutral. Number of protons equals the atomic number. So if I have carbon 614, then the number of protons is equal to 6. The number of neutrons can be found by taking away the number of protons from the mass number, because the mass number is the number of protons plus neutrons. All atoms have an element of the same number of protons in the nucleus. It is unique to that element. If I had another proton, I don't have carbon 14 anymore. I now have nitrogen 14. We have to know the masses, charges, and location of each of these subatomic particles. Now, what is current? Basically, if I get something negative and I put it next to something else negative, this negative thing will repel and that negative thing will repel. If I get a cell that has got a negative side and a positive side and I put an electron next to it, the electron will repel. An electric current flows when electrons move through a conductor, such as a metal wire. Electricity passes through metal conductors as a flow of negatively charged electrons. These electrons are free to move from one atom to another. It is a sea of delocalized electrons. So this electron can move wherever it wants. It can go there, it can go there, it can do whatever it likes. If I add a negative charge to that side of my wire, then this electron will repel into that electron, into that electron, into that electron, thereby creating current. Now, we have two different types of current. But if I look at a cell, the long line is the positive line and the short line is the negative line. Conventional current goes from positive to negative. We defined current before we discovered the electron. All we could observe was that there seemed to be positive things moving from the positive anode, the positive node to the positive terminal, pardon me, to the negative terminal in that kind of a direction. However, that's not what's actually happening. We then discovered the electron and realized that electrons make electricity. So it's these little electron charges that move from negative to positive, but we have to use the conventional current rule for most of the rules of electricity. I have to know the circuit symbols. Please learn them, especially this one, and 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 this one. Yeah, all of them. It seems like a lot, but it's not. Write them out 20 or 30 times and you'll never forget them. Some terminology then. Current is the rate of flow of charge in a circuit. So the equation for that is I is equal to Q divided by T. Potential difference, also called voltage, is the difference in potential between 2 points in a circuit. So if I have got a bulb and I put a voltmeter around said bulb, and I know that there is a potential of, we're going to say 4 just for now, here and 2 there. I know that 2 bits of potential have been used by my bulb. Therefore, I would say it's 2 voltage. Now, what do I mean by the potential between 2 points in a circuit? It's the difference between the positive and the negative charge. They're also known as the amount of energy per coulomb of charge. So if this coulomb of charge here has got 4 joules and this coulomb of charge here has got 2 joules, then I know that 2 joules was used by my bulb, which is the same as saying 2 volts. The volt is the joules per coulomb, the amount of energy per coulomb of charge. Charge is the amount of electricity traveling through a circuit. It's the amount of electrons. One electron by itself is useless. A packet of electrons is much more useful. Resistance is anything that slows the flow of charge around a circuit. It's usually caused by electrons colliding with ions in a material. The electron collides with the positive nucleus. The positive nucleus vibrates more, causing an increase in kinetic energy. The increase in kinetic energy increases the thermal energy stored. It also increases the amount of resistance. I'm sorry about these lines. I don't know what makes them happen. I'm going to draw 2 bulbs in a series now. The electrons will flow through one and then through the other. So my electrons are moving around this wire in that direction. The electrons will flow through that and then flow through that. A parallel circuit, however, has got branches so that electrons can flow simultaneously through these bulbs. One electron will move down that particular branch, another electron will move down this particular branch, and the energy is transferred identically. Consists of components that are connected one after another. It can also be called a cascade connection, meaning the electrons go through one bulb into the next. The current that flows in each component connected in series is the same. If I set up an ammeter here and an ammeter here, if the amps is there is 1, the amps there will be 1 as well. If this lamp breaks, then the entire circuit will go out. Parallel circuit consists of components that are connected in different branches of the circuit. Now, this is one branch, branch 1. This is another branch, branch 2. This branch is in parallel with this branch. However, this bulb is in series with that bulb. So this is a parallel circuit with 2 series bulbs in parallel to 2 more series bulbs. If this bulb breaks, then this bulb will not work, but these 2 will. If I add more branches on, I've got more current. Imagine we've got lunch queues. We've got Billy here who's lining up to get his lunch from this place here. And we've got a whole load of students all behind Billy. If there's only one place where Billy can get his lunch, then everybody has to wait their turn. It will be slow. If I open up another place for the next person to get their lunch at the same time, then it will be faster. Same thing for current and circuits. How do we measure current? We measure current using an ammeter. The symbol for that is a capital A. The unit is an ampere. Oh, it's actually an ampere, but that's neither here nor there. And it is shortened to amps. We use an ammeter to find that. The ammeter is always connected in series with the component. Potential difference is measured in volts. If I want to find the voltage of this particular bulb here, I've got to connect it in series. It will measure the potential difference going in, it will measure the potential difference going out, and it will find the potential difference that was used by this bulb. Potential difference is the energy transferred per unit charge passed, and therefore a volt is a joule per coulomb. Get rid of that. You can read it if you want. In a series circuit, the current will always stay the same. So if it's 2 amps here, it's 2 amps here, it's 2 amps here. The reason for that is one electron cannot go faster or slower than the electron in front of it. So this electron will repel into that electron, causing it to repel further. No one electron can skip around the next one. It just is what it is. In a parallel circuit, though, we can get different amounts of current. At this junction here, there can be a split of the amount of coulombs per second. So this is 6 amps. This means I've got 6 coulombs for every 1 second of time. This is 4 amps, meaning 4 coulombs per second are passing through that branch. This is 2 amps, meaning 2 coulombs per second are passing through that branch. The total amount of current entering the branch is always the same as the amount leaving the branch. If there's 4 coulombs per second here, there'll be 4 coulombs per second here. If there's 2 coulombs per second here, there'll be 2 coulombs per second there as well. And they will also meet back up, so the electrons will flow from negative all the way around my circuit, back in again. There will be a split here, but my electrons will eventually make it back to the junction, making the total current going in equal to the total current going out. Well, going into the cell and out of the cell. We say that current is conserved. This means that the current doesn't change overall. It's still 6 coulombs per second overall, but there can be changes in branches. When charged particles move, they form an electric current. Electric current is the rate of flow of charge. I'll write down that equation again. I is equal to Q divided by T, the number of coulombs per second. Charge is a property of a body that experiences a force and electric field. What does that mean? It's a property. It's a fundamental thing. Electrons just have charge, and it experiences a force and an electrical field. So the amount of charge, the rate of flow of charge, is just referring to the electrons themselves who have got a fundamental property that they can be affected by a force in an electric field. The amount of energy transferred by electrical work can be calculated using the equation E is equal to Q times V. Remember, electrical work is a transfer and measured in joules. Here's an equation for you to try. And another. Oh no, it's not, pardon me. For electrical charge to flow through a closed circuit, the circuit must include a source of potential difference. If I just have wires with a bulb, they will not work. I must have some source of potential difference. An electric current is the flow of electrical charge, usually electrons around a circuit. The size of the electric current is the rate of flow of electrical charge. In a series circuit, the current is the same at any point in the loop. This is the equation for charge. Q is equal to I times T. The reason why we use the symbol Q is because it's referring to the quantity of electrons. More electrons makes more charge. And the symbol for current is I because it stands for intensité du courant. André-Marie Ampère was the chap who discovered current, and he used I as the symbol to mention, to symbolize the intensity of the current, the rate that the current is moving. If current goes up, if I increases, it's got a more intense rate of flow. If I decreases, then it has a less intense rate of flow. Here's a question. And here's some more questions. And here are your answers. Okay. The current through a component depends on both the resistance of the component and the potential difference across the components. So resistance slows down current, and potential difference is what's necessary for current to occur. The electrical resistance of an electrical conductor is the measure of the difficulty to pass a current through the conductor. The greater the resistance, the smaller the current for a given potential difference. This is a variable resistor. It can also be called a rheostat. And you can change the resistance. By sliding this up and down this long twist of wire, you can change the resistance that is in a circuit. This is the symbol for a variable resistor. I've seen it come up about 3 times in past papers. A variable resistor is a component where the resistance changes as you slide the connector along it. It can be used to investigate how the resistance of the lamp changes as you change the resistance. Of the circuit, perhaps? Yeah. Yeah, okay. This is Ohm's law. Ohm's law can be written down as V is equal to I times R. Very common little equation this, make sure you know it. The only other one that's as common is the power equation, P equals I times V, and EP and EK are the two very most common. The resistance in a circuit will depend on the components used in the circuit, as well as the length of the wire used in the circuit. The longer the wire, the greater the resistance. Here's a question. I mean, of course it's a question. Okay, some rules that we have to know about these. And there's a video explaining this all by itself. There is a link down below where you can look at that video. Series circuits consist of one loop of wire. There's the same current through each component, and the total potential difference of the power supply is shared. If this is a 6-volt cell, and if this is a 3-volt bulb, and this is a 2-volt bulb, this has to be a 1-volt bulb, because the total amount of current must equal, the total amount of voltage, pardon me, given to each component must equal the total amount of voltage that's in the cell. The current is the same through each component. The potential difference is shared. And the total resistance is the sum of all the resistance. So let's say this has got a resistance of 15 volts, this is a resistance of 5 volts, and this is a resistance of 1 volt. Total resistance, R total, will equal R1 plus R2 plus R3, ... meaning that the total resistance will equal 15 plus 5 plus 1. 21 ohms will be the total resistance. In parallel circuits, things are slightly different. The potential difference across each branch is the same. So if this is a 6-volt cell, there will be 6 volts going through this, 6 volts going through this, and 6 volts going through this branch. The reason for that is that 1 volt is equal to 1 joule for every 1 coulomb of charge. I'm going to write this as 1 volt is equal to 1 coulomb carrying 1 joule. If I have got a coulomb of charge carrying 6 joules of energy and it travels down that branch, it will give 6 volts of potential difference to my lamp. If this Coulomb goes through this branch, it will give 6 volts of potential difference to this. It does not matter which branch my Coulomb goes down, it will still be carrying 6 joules of potential difference. In a series circuit, if I have a Coulomb of charge carrying 6 volts, this Coulomb must first travel through this bulb, then this, then this. It must share out its voltage at each of those bulbs, meaning that each of these bulbs will get a little piece of the 6 volts. In a parallel circuit, the Coulombs will split at a junction, but they will still have the same amount of energy. The potential difference across each, not each component, each branch is the same. The total current through the whole circuit is the sum of the currents through the separate components on each loop. What does that mean? If there is 6 amps of this in this ammeter, 6 amps in this ammeter, and 6 amps in this ammeter, I add them all up, and that will give me the total current in my circuit. And the total resistance of 2 resistors in parallel is less than the resistance of the smallest individual resistor. 1 over R total is equal to 1 over R1 plus 1 over R2 plus 1 over R3. So let us say that this resistance is 10 ohms. It isn't right, okay? It's not matching up the numbers. It doesn't really matter. And this is 5 ohms. If I wanted to find the total resistance, I would do 1 over 10 plus 1 over 10 plus 1 over 10 plus 1 over 5 plus 1 over 5. So that'll be 1 over R total is equal to 1 over 10, so it's 2 over 5, 5 over 10. Invert and multiply. Total resistance will equal to 2. This rule you have to remember. You don't have to know the whys, you just have to know that it is. The total resistance of 2 resistors is less than the resistance of the smallest individual resistor. How do we measure resistance? To measure the resistance, you need to set up this circuit with an ammeter and a voltmeter. You can then get your voltage and your current, and you can find your resistance. By measuring the current using the ammeter and the potential difference using a voltmeter, the resistance can be found from that, R is equal to V divided by I. The electrical component tested can be changed from the resistor shown to any other electrical component, say it's a bulb. To get a range of potential differences and currents, a variable resistor can be added into the circuit or the input potential difference changed. What does that mean? Use a power pack. A power pack, you can change the amount of potential difference that's going in by twisting the dial. Or I can use a variable resistor. If I add a variable resistor here, I will either increase the resistance or decrease the resistance, thereby increasing the voltage or decreasing the voltage that's available for my component that I'm testing. There are different kinds of resistors. An ohmic resistor has got a fixed value. It does not depend on the current. An ohmic conductor that does not change its resistance can also be called a fixed resistor. The current through an ohmic conductor at a constant temperature is directly proportional to the potential difference across the resistor. What does that mean? Straight line. The same increase in potential difference will get the same increase in current, and this value, the value for this resistor, will not change. It is a fixed number. A reminder, please, that 10 volts is the same as minus 10 volts, except it's going in the opposite direction. So this circuit would have, say, plus 10 volts, because that's the direction the current is going now. If I change this around to make this the positive and this the negative, it would be minus 10 volts because the current is now going in the opposite direction. So plus and minus voltage just refers to direction. So down here, I've got minus 6 volts, minus 3 amps. It's the same thing as plus 6 volts, plus 3 amps, just in a different direction. They will make a straight line IV graph, I standing for current, V standing for voltage, that goes through the origin. Non-ohmic conductors like filament lamps, the resistance changes. The resistance of components such as lamps, diodes, thermistors, and LDRs are not constants. It changes with the current through the component. In a filament lamp, as the current increases, the temperature increases, so the resistance increases, which means we initially get this fairly proportional increase in current until we get a nonlinear relationship. This nonlinear relationship means that even though there's a much more potential difference, the current is not able to keep on increasing at the same rate because resistance has increased. Diodes have got incredibly high resistance in one direction and almost no resistance in the other direction. Almost no resistance in the other direction, meaning for a very tiny amount of voltage, you can get a very high amount of current. They're components that allow current to flow in one direction only. Current can only flow through the direction the arrow is pointing. It cannot flow in the direction with the little wall. Oops. Now, most thermistors, when they get hot, increase their resistance. The only one we need to know that doesn't is a thermistor. The resistance varies with temperature. As the resistance of the thermistor decreases as the temperature increases, and that is weird. We use thermistors and thermostats to control temperature in our house. Light-dependent resistors, or LDRs, that are types of resistors where the resistance varies with light intensity. As I increase the light level, I decrease the resistance. The resistance of an LDR decreases as light intensity increases. They're used for like turn on street lights when it's dark. It's not a little person with a switch. It is an automatic circuit. Everyday electrical appliances are designed to bring about energy transfers. And remember, an energy transfer is moving something from store 1 into store 2. Store 1 and store 2 don't do anything, but it's the transfer. It's this little thing here that forces the electrical work, the heating, the radiation that actually does something. Energy transferred is another term for work done, and it is measured in joules. The amount of energy an appliance transfers depends on how long the appliance is switched on for and the power of the appliance. The power, and we'll come on to this in a second, is the amount of energy divided by the amount of time. 1 watt is equal to 1 joule per second. Electrical appliances convert electrical transfers from the AC mains or from batteries into more useful forms. For example, motors converting electrical transfers into kinetic energy. Light bulbs converting electrical transfers into light transfers. There's no such thing as electrical energy or light energy. They're transfers. Light transfers energy from one store into another one. Electricity transfers energy from one store into another one. Electric heaters converting electrical transfers into heat energy stores. As with any energy transfer, some energy will be transferred usefully and some will be wasted. Electrical energy. Right. Electrical transfers cause dissipation of thermal energy to surroundings when an electrical circuit does work against electrical resistance. All electrical circuits have some resistance. This is because when electrical energy is passed through a resistor, it does work against it. The energy transfer is a result of collisions between free-moving electrons and the metal ions in the lattice. When a current is applied, energy transfers in circuits can be reduced by using low resistance wires. Not friction. And also, there is no collisions between my electrons, okay? They repel each other, so we're not going to get repulsions. Heating effects can be useful or they can be unuseful. This is a plug. This is hot. That is bad. We do not want our electrics melting. However, we do want our electric ovens getting hot, our kettles getting hot, our hair dryers. What's this? What's a hair dryer? Never heard of that. And what's an electric fire? We want those getting hot. We don't want computers, televisions, chargers, and plugs getting hot, so we need to reduce resistance, because when a negative electron collides with the positive ion in the lattice of the wire, it will cause it to oscillate more. As it oscillates more, it will increase the kinetic energy. If it increases the kinetic energy, it will increase the thermal energy, which will also increase the resistance of the component. More resistance means more thermal means bad. Here's an equation, E is equal to I times V times T. And here's an example question. Here's the equation for power. Power, 1 watt, is equal to 1 joule per second. Energy transferred by an electric circuit depends on the time taken for that change to occur. Power is the energy transferred by electrical devices per second and is measured in watts. 1 watt is a transfer of 1 joule per second. This is the equation, P equals E over T. It can also be written down as work done or electrical work done divided by time. Here's a question and answer. Watch out for this, okay, folks? Minutes, watts, kilowatts, just kilojoules. Make sure that we get the conversions correct. Power. When electrical appliances are connected into a circuit, energy is transferred to the appliance. The rate at which this energy is transferred is the power. Remember, rate is whatever is happening divided by the time taken for that to occur. There are two equations we need to know, P is equal to V times I and P is equal to Y squared R. You can write this as this. You can write this as this as well if you want. These two equations will be given to you. Here's an example question. Okay, here are some questions. Now I'm going to try some. I tried 5 seconds without speaking last time. Now what I'm going to do is I'm going to do it quicker, but I'm going to draw on a little bit. Just ignore the squiggles; they're just there to get it. Core practicals online using PhET Colorado, which is the best website in the entire world. Okay, there's a link for that down in the comments information section. I don't know what to call it, but it's there. So we're going to build a circuit shown in the diagram. Actually, do you know what? I'm going to leave this up here for you to look at. Watch the video, look at this. You can read this in your own time, and then try and do the experiment. So I've explained this in the video. There's a Pearson video for it. Here are just some questions. So I'm just going to give you the time to do it. Read it if you want to. Read this if you want to. Read this if you want to. Do these answers if you want to. Do this practical. This practical does get a bit confusing, so it's worthwhile spending time on it. Okay, it's this difference between a nice easy series circuit and this difficult parallel circuit. Try this. Do that. That's good. Ooh. Here's some more questions. Here's some more questions. Voila. Okay, thank you very much, everybody. Whoa. Okay, thank you very much, everybody. Any questions, pop them into the comments or send me an email. Bye-bye. Oh, every time. Bye.